Hi everyone, welcome to another Common Lisp Study Group. I'm your host Ron Vadum with Atlanta Functional Programming. Welcome to our ninth installment of our CL Fourth series of building a fourth interpreter inside Common Lisp. A couple announcements before we begin today. We're going to take a brief hiatus for 3 weeks, starting next week for the summer, end of summer, kind of like I'm going to take a little vacation. We will resume September the 12th. I've already updated the meetup page for folks who are subscribed to our meetup. Those of you who are not, I encourage you to go to Atlanta Functional Programming for updates on meetups and upcoming talks. In addition to that, folks who are in the Atlanta community, or folks who want to give a talk in general as part of the AFP meetup, please contact me. I'm available as Bugram on Functional Programming Slack, or contact Jed Taylor, who's available as Dagmar on Functional Programming Slack or Discord. I'm also available on Discord as well if you want to talk and provide some ideas and additional talk topics. Today we're going to be discussing kind of the end of this fourth interpreter. Just a quick review for folks who did not join us for episode 8 that was sudden last week. We went ahead and fixed in this branch, which I just realized I should have merged in to master because it's complete now. There's a couple of things that we added. Primarily, we fixed our issues with the if statement, if then pair. We realized, and this was kind of reviewed in the last episode, that the if then pair is primarily used, and its primary purpose is for metaprogramming. Can be used for the equivalent of what we would call fourth macros, although they're just compiling new words into a dictionary. And we added 3 new statements, primarily the else statement, as shown here. Begin and again. Begin and again, if you recall, was the way you would implement looping logic inside your meta words in fourth. We then used those, if you recall, to implement a couple of examples. Just quickly, the countdown example, where we ended up just simply showing you that we can go ahead and use these constructs in a interesting fashion. This is a very simple case of the begin again example that was brought up last time, and there was an additional example as shown later on, where we went through and showed that with it, if and then, you can mix the two up and do some interesting metaprogramming in fourth. Primarily, you can actually preempt looping by simply engulfing the again, which will branch off and bring you back to this begin for the next looping within an if-then block. So if you specifically look at this piece of code here, you will notice that once the conditional turns to nil, it will automatically skip these 4 statements and then go up here and drop the result from the parameter stack and then move on. So give me just 1 second here. All right. So today we're going to begin our discussion on where do we move from here exactly? How does this allow us to start implementing stuff and specifically compile our fourth code directly has Lisp functions that can then be implemented in um, that can then leverage the full features of the underlying Lisp compiler that you're using to optimize the code and run it at runtime. This is particularly useful if you want to take, fourth code that you wrote in Lisp, and you want to integrate a fourth interpreter in Lisp, but still get the same performance as the Lisp uh, compiler has normal native Lisp code itself. To begin with, before we start going down that route, I want to touch on one topic that was brought up here in the in the book. Two topics. One on full recursive functions, as well as some more introspection and underlying explanation of some data structures that we've introduced in earlier episodes. To begin with, we're going to first look at two new functions that were brought up in the book. And these were more refactorings of patterns that we were using when we were debugging our fourth code earlier. This is going to be particularly useful when you are going to start doing the fourth to Lisp transpilation. The first function is primarily called getFourthThread, which I've actually just implemented earlier. I'll just show this to you accordingly. This function basically is nothing more than the pattern that we've already been using in past episodes. Primarily, we are using the Pandoric macros to actually go into the fourth interpreter in question and look up a particular word in that fourth interpreter's dictionary to see if the fourth word is available. Fourth word thread is available. And then we try and go ahead and use an additional auxiliary function called printFourthThread to be able to print it out using the circular logic. If you recall, print circle is a global variable in your Lisp environment that allows you to take recursive definitions and conveniently structure them so that it could print print them a little easily in your Lisp environment. The main reasons we would want these is primarily to be able to introspect and return and investigate structures of the fourth threads that we've generated up until now. So, to give an example of this, I went ahead and created, got this from the book specifically, an example of actually defining a new fourth environment with square 3, with the square function, and then obviously this is going ahead and squaring 3 and printing it out. A very simple thing like this. When we go ahead and run this guy here, we'll see, and for the folks wondering why I didn't have to compile this here, I compiled this earlier when I loaded up the Lisp code into the REPL. So this is already compiled code. When I run printFourthThread here, you can see that it's referencing the original lambda function that was originally defined when the function was defined. And it uses standard reader macros, and we've seen this in other episodes of referencing reader macros, to actually go and reference this guy in elsewhere when there's making a particular recursive call. Now this is mainly for The circular logic being done by duplication and by what's it? Um, I think it's the print logic, if I'm not mistaken. Yeah, that's what it looks like it's doing. Um, and this is particularly useful just again when you are leveraging and you want to go and look through particular fourth words and fourth thread blocks. We'll use go get fourth word and print fourth word later on when we start further implementing some of the final functions and reviewing some of the final pieces of our forth to Lisp transpiler that will compile forth code. Um, so up until now, when we started talking about recursions and recursive functions, this is segueing into our second topic here before we start talking about the other Lisp pieces, is when we were talking about recursive functions in past episodes, we've the book and kind of defined a lot of the recursive functions that we presented so far as being more um, tail recursive at first, and the biggest example that we used was branch if. Now we want to be able to though at some point, and there are use cases, especially when we're compiling forth to Lisp, that we want to be able to have the word um, being able to call itself um, using just whatever normal threading mechanism that we've already built into Lisp, and I mean, sorry, into Forth. If you recall, the threading mechanism is all these different code blocks that are able to reference themselves, and we could actually interleave different threads or different code blocks with each other. But one of the reasons why before we were unable to do that is because most of the time when we were implementing our functions, we were using branch if. But more specifically, we were following this pattern where we created an anonymous function using getting out of compile mode, writing a series of words, exiting out of it, and then naming that new created word after the fact. So because of this particular structure, as you would see in our square example, being put into place, recursive functions were a little bit problematic because of the fact that, especially if you wanted to recurse ahead of time rather than later on, there's no way to recurse because this particular code block didn't have a symbol, a name associated with it. So when Forth actually goes and tries and look it up, it doesn't exist, and it will start, complaining. So how would we go about and actually, you know, get ourselves into a position where we can do proper uh, full recursion? Well, if you recall what, and we'll go through this example of the full recursion for factorial in a minute, but if you recall what this curly brace actually means, we'll get some hints at what exactly we need to do and go and implement that, as you can see in that code example first. So what does that curly brace mean again? Well, that curly brace was nothing more than an alias to create. Specifically, in our standard library, we basically used the left curly brace to indicate that we're getting out of immediate mode. We're creating a new word. We're going back into immediate mode. And then we get out of it again to actually go in and label our um, our our anonymous function has the left curly brace here and added it to our dictionary. Recall the differences between square bracket, left square bracket, and right square bracket, which is we defined way earlier. To being getting in and out of immediate mode here. And remember, the left curly brace was actually getting us out of this unconventional. Oh, okay. The square bracket means we're not in immediate mode when you're doing left, and the left square bracket means that we're not in immediate mode, and the right square bracket means that we're not in immediate mode. So, sorry, let me repeat that. The left square bracket means that we're in immediate mode. The right square bracket means that we're not in immediate mode. This is something that we can leverage to actually get in and out and label stuff and interact with our fourth REPL at runtime. So the example that we're going to cover here is how to define factorial using this kind of thing. Well, okay, how do we define factorial? Well, before we start talking about defining factorial, first what we're going to do is just check to see if that we can create a new word in here. Well, what's creating a new word? Creating a new word is either using the create statement directly, or what you could do here is use left curly brace to say that you're going to start a new anonymous word and that's being defined. At this point, on line 556, the word has already been defined, but now we want to label it so we can actually go and use it in recursive calls. So to do that, we need to go into immediate mode, directly execute fact and name so that the fourth dictionary gets updated and that fourth word at the top of the stack is associated with the factorial. Go back into non-immediate mode and start metaprogramming. We start defining this function as being, hey, we're going to do standard factorial. We subtract 1 from it. We check to see if it's still greater than, and if it is, we'll call the factorial. Otherwise, we'll multiply this. Now, and if you recall, this here is going to, just go and define, 5, 4, 3, 2, 1 accordingly. And we can even see this if we just simply, then just do, what is it? We do a dupe print and then times. We could define it that way. So if we try and compile this, you'll see that we'll start with 1, 2, 6, 24, and 120. Our final things, obviously, factorial of 5, which is 5 factorial is 120. So this is a way of actually leveraging what we've already defined in getting in and out of immediate mode to creating full recursive functions. But let's go look at the structure here of the recursive function, shall we? In fact, let me do this. Let me do that this way. It's a little bit cleaner. And let's do this again. Okay. Now, if you look at that, you can see that 2 will represent our dupe primitive that's written in our dictionary. And you can actually check this out by simply looking at matching what's in the code with what you're seeing on screen. So this first line here is dupe 1. This is going to be minus here, and then we've attached 2 to be dupe again. And anytime you see a duplication of this is just simply associated with this particular closure instance here. This way, it's easier. When you use print fourth thread, it essentially uses the print circle reader macros to actually go in and label some of these functions to make it easier to go and debug particular S expressions. The calls to number one is obviously direct calls to itself, and then otherwise we're calling the multiplier here, and this is just a closure of additional functions that are anything that's within the actual closure itself is related to a function call related that's in other parts of this particular structure. So reading through this, each one of these closures is labeled a particular way. It takes a little bit of getting used to when you're reading some of this print circle statements, but I encourage you to, especially folks who are watching this after we broadcast, go back, pause the video, and then work your way through actually seeing how these assignments to these individual closures match to the particular primitives that are in the high-level code to get an understanding of what the structure actually talks about. The one thing, though, that is obvious from this structure that I'm sure folks can see pretty clearly is that this is a very standard Lisp structure. It looks very similar, like a normal Lisp program that we would write ourselves, minus the additional closures that are around there. Because of the abstract machine that we've defined, and our understanding of the abstract machine and how it's executing these threads, we can leverage this to actually go in and compile this fourth code in such a way that it can be leveraged by the underlying Lisp compiler to create native Lisp code, or in the case of Lisps like XBCL, where they can compile Lisp functions to native machine code, you can actually use that to compile machine code for your given platform for that particular fourth program. The book calls this flubification, just because he defined like the blub paradox. Flub has something being the difference between being fourth and non-fourth, and being a little bit more bloated than what fourth provides. So we're going to go ahead and implement this transpilation process, which allows us to compile our code directly from fourth to Lisp. My apologies for the little noise there. So what can we do for this? This is what's the exercise for the remainder of today's episode, and until we actually get this all up and running, hoping we can get this done in a pretty quick fashion. There's a couple of functions. The order in which it was written in the book and written in the code elsewhere that you might see in the let over lambda code that is available online is going to be slightly different than the way I'm going to present it here, because the book has some of the helper functions defined after the actual core functions being defined. I'm just going to go ahead and reorder it slightly so that it's easier for you to know what we're building. Just give me 1 minute here. Okay, so 19. Okay. So the first function that we're going to be defining is a simple macro called assemble flub. Assemble flub basically takes a hash table that's defined elsewhere. That's going to be a list of labels of that were populated, and it's going to check if a previous pass of the force code reference as one of these goes. And specifically, it's going to be it's referencing a location that we're currently compiling. It's going to then use that to return a it's going to return the following. So let's go ahead and write this. It's going to take a form and the rest of the code. And what it's going to do is it's going to check to see if we have this in hash table. And this is going to essentially implement kind of like the recursive piece of the compilation for the current pass of the word that we're compiling. It's going to return a list star of a couple lists. So this is going to take in the current code that we and get hashed. These hash tables are going to be holding actual Lisp code. And at this point, we are now at a point where we can actually describe one additional abstract register that I'm sure many of you may have forgotten that we've defined early on in previous episodes, but is available, and that is the D-table abstract register. What is this D-table abstract register that's in our Lisp code? And I will show this to you in just a minute so that you can see what it is that we are leveraging. So, if you recall D-table, this is an abstract register. Yeah, thank you. An abstract register that maps a fourth word to the list structure, that is the Lisp list structure that created them. At the time, that fourth was created, the fourth interpreter itself was created. So this is populated when we're actually calling, when we're calling new fourth interpreter. Because if you recall, the new fourth interpreter is creating each of the dictionaries, and these dictionaries are holding all the fourth words that are being compiled in real time. It's at that time that D-table is actually getting populated. We're going to leverage this D-table later on because to grab these list structures, as we were seeing here with the symbol flub. There's another thing that I'm going to be mentioning here that the book kind of mentioned, and so that we don't get any additional questions. Some of the code that's going to be written in this last Lisp piece is going to make heavy use of tag body and go-tos rather than go forms rather than using our inner interpreter, because we want to actually remove the need for that inner interpreter when we're building it. Especially, and this is mainly because what the inner interpreter is leveraging when it's compiling the fourth code, specifically the use of a return stack to keep track of whether or not we are calling a particular function. Recall, the stack-oriented structures that we're using inside of our fourth interpreter don't actually although we've implemented them, they don't actually exist in terms of how Lisp code is being compiled. So we have to take a different approach to actually transform our forth code into this Lisp code. So using this assemble flub function that we're that we just defined here, what we're going to do is we're going to define another function, another macro actually, called flubify auxiliary. This is an auxiliary function that actually is going to be leveraging this guy pretty heavily in this assemble flub guide, pretty heavily in order to take in a piece of forth and convert it into the appropriate Lisp structure that it needs to represent. One thing that this is going to take advantage of, as we will soon see, is it's going to leverage anaphoric macros to actually take advantage of the fact that every non-primitive word is surrounded by a particular tag body and can use gensims as tags rather than words. And this is pretty useful for us when later on when we're actually leveraging this function in another function called flubify. Yeah, I think it was flubify that used it. Yeah, flubify is the one that used this. All right. Okay, so let's go ahead and implement this guy and see what happens. This is anaphoric, a lambda, and we go ahead and do this. I don't think this I was reading this through this code the other day, and I'm pretty sure that this code does not necessarily need to be an if statement. It could be just a simple when, but I haven't tried playing around with this just yet to see if that's the case. When I was reviewing the book the other day, I wasn't sure how to structure this, so I thought I'd just show you guys in real time as if we're going through this. Hopefully, folks who are watching can correct me accordingly. Okay, so this guy is going to call assemble flub, do a fun call that gets the hash of the card key from our primary hash table. Here. And then what we'll do is we're going to use the anaphora to actually go in and grab the cutter, this guy. So now we need to check to see, or in another case, get hash, see if it's in the particular thread hash table. Sorry, not thread empty. And if that's the case, then what we're doing is we are assembling the function call to get hash rc thread ht. And we'll check if car C is branch if. If it's a branch if, then we're doing something slightly different. Mainly what we're going to do is we're going to assemble flub with if up p stack go get hash stored in the hash table in the Go tags. If this code doesn't look, if you're not understanding what this code is doing as we're going along, don't worry about it. We will review this once this is all in place. Okay, and then we go over if it's a console. If that's the case, we're going to have to call Flubify on our fourth interpreter. Parse HT and HT and what we'll do here is we're going to go ahead and return self. Then we have a default case where we just simply assemble the flub associated with the code of pushing something onto the P stack. And okay, cool. So this is kind of the structure that we're going for. Let me see if I can get this entire, yeah. What this is doing is kind of the equivalent of what our top level interpreter is doing. It's grabbing all the different cases of from our D table, and it's creating the appropriate function calls behind the scenes for the code that it is executing. You could think of this as roughly the equivalent as, at least as I understood it, it's going to be roughly the equivalent as the inner interpreter that we used before. And the difference is that the output of this is going to be a bunch of Lisp code that's going to be compiled later on, instead of something that gets executed in real time, interactively. I mean, like it has a normal interpreter. Now, let's just make sure this all compiles. This looks like it's all compiling. This function, Flubify auxiliary, is used by Flubify, and you saw Flubify is actually being called in this code too as well as a recursive call. It's making the next hop, so they're kind of self-recursive there between each other up until they hit some sort of base case. And what Flubify does is it's a normal Lisp function that takes the fourth interpreter that we're leveraging, the current thread that we are compiling, the two hash tables that we're kind of reconstructing. One is the primitive hash table that's representing all the fourth primitives that we already have some predefined structures for, and the code block hash table of the piece of code that we are currently compiling. Additionally, it also takes this parameter called branch if, which I'm not sure if is, let me just go and double check this. It says it's a function that does the first pen is checking for branch if instructions. Right. Right. So the branch if parameter basically checks to see if there's a series of branch if instructions, and if there are, it'll build up the Go hash table that we'll we'll leverage later on in calls to Flubify augs. So let's see what this function does behind the scenes. So this, I've never seen this actually work, but when I write code like this, if it doesn't, we'll figure out another way of handling this. Get hash the thread for the thread hash table. Set f hash one hash list of a single Jensen. Then what we're going to do is we're going to make our hash table of Go labels. These are actually what's going to be used to construct the tag bodies that are going to, jump, set up our jump structure when we're actually building up our Lisp code. And then what we're going to be doing is we're going to fun call the word macros a lambda that C, do this, and we're going to check to first see if it's equal to branch if, and if it is, what we're going to do is we're going to set up the hash of the current code that we're compiling catter to the Go statement with a new symbol. So here we're actually constructing we're adding a new label to a piece of code that we're going to end up referencing later on. Otherwise, we're going to do const p rc, and then we're going to make calls to Flubify. Fourth thread, our primitive hash table, our current thread hash table, and then branch if. Otherwise, it's going to be the thread. So what this does is, so what this piece of code here is on the current code block that we're compiling, it's going to go and construct all this. It's going to execute the lambda function to see if it's a branch if or it's something that it needs to construct a Go label to, and then call Flubify on later on. Then what we would do is we would attach this to the piece of code that we were looking at earlier. Now, for folks who are paying very close attention, you will see that essentially what that #1 hash is nothing more than a reference to the entry to our thread hash table. So if this actually does not work, what we could do is we could replace it with that get hash directly. That's just a reference variable that's being used later on. Okay, let's see. Flubify aux and the thread. Okay, I think I got it all. Okay, that compiled. Let's make sure. One minute. Okay. So what's the next thing? Oh yeah, so the next thing is compiled hash table. So what this Flubify function does is this is essentially building up the labels to our primitives, our code blocks, and and for branch instructions specifically, it'll attach the appropriate tag body and labels to another hash table called Go. We'll call him Go HT for this. This hash table is still in Lisp. It's just normal Lisp code. It is not code that. And hold on 1 second. Let me just make sure that there's undefined. Oops. 1 second. This should be. That. Let me just make sure. Undefined. Yeah, of course. That's a. Unless we compile it to the top level, we're not going to actually leverage all that. Okay. So this is all just normal Lisp code in an appropriate hash table. So we still need to compile all this code, and this is where a function called compile Flubify comes in. It's basically going to take in, and let's define this guy, compile Flubify. It takes in the hash table that we provided for a given code block, and a particular code block, a fourth thread that is, and it converts it into essentially a labels function that can then combine all the flub threads together, the word threads that we just converted, and then goes ahead and calls it. This ultimately will then, behind the scenes, compile the Lisp code into a particular Lisp function. So let's see how this works. This is going to take in our thread and our code, our particular hash table that Flubify created for us. And what we ultimately do is we create an anonymous function here through labels that will then, and it's not actually anonymous. It's defined by the the entry that's in the thread hash table itself, and you'll see how this looks in just a moment as we're writing this through. This code is ultimately going to get populated by just us map hashing through the actual thread hash table that we passed in, the specific hash table that we passed in from Flubify, and grabbing the appropriate key value pair and attaching it into this particular function. And what this is doing is very specifically is it is stitching together the different threads, and you'll see how it's doing this in a minute. It takes in, because remember this is a hash table that we're iterating through, so we're using map hash here instead of mapgar. We're going to grab the key value pair. We're going to ignore the key for the time being because it isn't really needed for the sake of this piece of code. And what we do is we essentially create a tag body through this value structure. Sorry, I keep pressing escape instead of backtick. And what this does is it's going to take. Remember, the key value pair of a particular thread in the hash table is actually a list of. It's a key with the thread name and associated with the fourth word, but the value itself is an S expression. It's going to be a list of associated things. So we can actually destructure it by using car and getter and what are our normal Lisp functions. So what this is doing here is it's just going to go ahead and push a tag body then we're going to just go ahead and collect. So if you see what this is actually doing is it's just taking in this stack potentially, and then it's grabbing all the collections from our hash table that we passed in by Flubify. All right, and what we return from this is going to be essentially the end reverse of this collection. This is one of our standard, ways of in Lisp creating a collection and returning it. You could go ahead and push it like onto a stack, which will be pretty quick. Then you could just use end reverse to go and return the value of the collection after reversing it. And what we use in here is we take this this labeled function, which again it's labeled through the thread of the tag body that we just defined, and we call it. All right, by just doing get hash thread HT. Okay. Oops. I forgot this. Thread HT. So now we defined how to we compiled our code. We went ahead and we call it through the normal thread block, which is also flubbified associated with the same flubbification process. But we're not completely out of the woods yet. There's two more functions that we need to define. One is this the fourth thread structure is such that there might be certain redundant fourth threads available in the code and unused fourth threads still structured around in the code. And we need to remove some of those before we actually go through the final process of actually converting it to Lisp. And that's going to create effectively, we need to effectively shake them off. So there's a thread shaker that essentially recursively looks at all connected threads, and it only returns the isolated relevant fourth thread structure in order to execute that given thread with our get fourth thread utility. And that's what's used to actually be, that's what's used by the Lisp compile function to actually go and compile the actual Lisp code, that final transformation. So let's see how this works. What does fourth thread require us to, pass in? So this is another function. This is not, notice, flubbify, compile flubbified, flubbify thread shaker, and our final Lisp function, our fourth to Lisp, are all normal Lisp functions. They are not macros. These are using what we defined, the two macros that we defined earlier, flubbify augs and assemble flub, to actually go in and convert that code to Lisp code. And for folks who wanted to see incremental running of this, unfortunately, I tried, when I originally looked at some of this code, I tried running it in the REPL last night, and you have to define all this up front before you you can actually see some code working. So please bear with me. The punchline is getting close. Thread shaker. What does this guy take? It's taking the fourth interpreter that we passed in, the thread hash table. Let's see what this guy's doing. So we have our thread, our hash table, our temporary hash table that we might use for temporary branches and such, our branch if, and whether or not we're compiling. Now, we're going to check to see if the current fourth thread that we are compiling is available in the temporary hash table. And if it is, then we just simply return from flubbify tree shaker with nothing. Okay. Otherwise, we're going to set. And what this is essentially doing is you could think of this as kind of like checking to see, as we're going through our tree, visited nodes. So now we go into the conditional. And again, this section here is essentially what's causing the shaking, because if you hit a visited node, it's just going to return from it. Otherwise, we're going to go ahead and do the following. If it's a const code block and the car is a branch, so that we just did, what do we do there? What we do is we have actually additional code in there. We cursively call the thread shaper on the cutter. Of the thread. Current primitive hash table that we're running on. Temporary hash. This is our visited nodes. This is the code block that we're running. And wait, did I mess up? Oh, I did mess up. That's right. Okay. We throw an error. And this will handle the case of us accidentally doing what we did last week, which is trying to metaprogram, use metaprogramming utilities like our if statement in a compilation world. Compilation word. Okay, so we have that. Then sorry, for some reason I had unbalanced parentheses. Now, the next case is if this is just a normal const thread that we can actually, so this is a code block that we could just straight up compile. In this case, we could just call Flubify tree shaper, or Flubify thread shaper. Let me do this. Okay. I only compiled it into initially just so that I could get some autocomplete of that function call when I'm typing. So, hash table. The temporary tags. We got the rank-if. And what we can do here is this primarily handles the list of list cases that we've been using so often in the inner thread case. The rest of the code. And if the thread doesn't exist, in our hash table, if it's a normal Lisp function, we're going to set the entry of the code block to, and object macros. We can do it. We're going to look itself up in the detail. And then we can attach that to the code so that it gets compiled. Alright, so this so this all compiled. Finally, we have our final code, which is forth to Lisp. This is the main thing that we would that engulfs everything that we've done up until now. And this includes everything that we did in past episodes too as well. This function here is what's going to ultimately compile our forth code into Lisp. So this guy is going to take forth, our forth interpreter, in the current word. Again, notice it is a Lisp function, it is not a Lisp macro. So we're not generating anything here. So what does this do? So this guy takes the given forth thread, it'll also create a shaker table that we're going to use later on, again, when it's going to generate our primitive hash table, our thread hash table, our branch if hash table, and it's not actually getting our branch if hash table, it's actually checking to make sure that we are using it's getting the thread code for the branch if. And this is what's being used later on for comparison purposes. And we're also making sure that we grab the code associated with compile, because again, remember, compile in the fourth sense is metaprogramming. It's going to be, its sole purpose is to set up a word for later on generation, in code generation. It's kind of what our Lisp macro stuff does. So we're done with what we need. And what we then do is we call simplify thread shaker on forth thread shaker ht. Our temporary hash table, this is just the hash table that's being used for visited nodes in the particular forth code that we're compiling. The code to branch if for comparison purposes to make sure that we create the appropriate transformations, and of course compile to make sure that we're not accidentally using code that should be used for forth code generation for Lisp generation. Once we do that, then what we will do is we will iterate through. Shoot, I did it again. We will iterate again on our shaker table. This time, we only need really the keys, not the values, because the keys represent the thread blocks that we want to leverage. And what we'll do is we will create a generated symbol for each one of those keys. And using that, we now have, so what we're doing is we're first, actually let me finish this code and then I will explain what we're attempting to do. Essentially doing that. Grab the same stuff from shared trees. Comma not inside of a back quote. Oh, that one. Right there. I think I got it, right? Yeah. I just converted it too. Right? Yeah, that's good. Okay. All right, so let's see here now. So what does this function do? Let's go through this function before we go through an example. This just so that we know what we need to start debugging if something goes awry. So force to Lisp basically takes a fourth environment, okay? And a word that you want to compile, okay? And it returns the corresponding Lisp code to execute that thread in Lisp, okay? Specifically, what it's going to do is it's going to first take that word and take the actual fourth environment, shake it, so that there's only those nodes that the relevant nodes that we need to actually do use to compile this particular word that we're trying to compile, and it will then iterate through, set up the primitive hash table tags that we want to go and flubify and create the code with, and it then ends up creating this piece of code. It generates essentially it takes the p stack from our environment, and it will actually write out the appropriate tags for that given piece of code that we want to compile and execute directly in Lisp. How might this look? This is kind of the test. So we've already kind of defined a couple of functions here that we could go and test with. Let's go ahead and use this this example here of creating square 3, right? So we saw what square 3 does. This is what it looks like when you're actually printing the fourth word here. But what does the code actually get generated for this? Let me just do this. This here, if we do fourth to Lisp, we specify new fourth in square 3. If we jump this, self is undefined. Why is it saying self is undefined? Oh, shoot. That's the anaphora, isn't it? 1 second. I gotta go check to make sure that I actually exposed self from the anaphoric macros package. If I didn't, for folks who are watching on the stream and folks who are actually in the Hangout call, you may have to do an update with the AFP LOL workshop to get those changes. So please, we have a little tangent going here, but bear with me. Let's see, anaphoric macros.lisp. Oops. Okay. Do I have self-defined here? Yes, I do. Okay. So the way that I'm going to have to leverage it on that other side is reference the package name. Lisp. No, I shouldn't have restarted. I should have just reloaded it. Oh well. Quick load. sure. Cool. Did I miss it again? There's probably another place where I'm referencing it. Level 5. Pairing yourself. Okay. Try this one more time. There we go. Okay. So when we look at this, unfortunately, this code that's getting generated, you have to recall what some of these pieces of code are. This is what essentially is the list structure that we've defined early on throughout this example, throughout this exercise of creating our fourth interpreter. Each of these represent the Lisp code that we generated that matches an appropriate operation. So for example here, this push car stack here, this push car p stack to p stack, this is the same as the duplicate function. And if we, just for reference, what we're doing is we're ultimately, that fourth to Lisp function is doing is taking each word, looking up in the fourth dictionary and saying, hey, what is your Lisp definition for this particular fourth word that's here? It grabs it and then it sticks it into it has an anonymous function that you would then end up leveraging later on when you're actually executing the fun call. And it does this accordingly for each word that's part of a particular fourth word that we're compiling. Okay, so if a fourth word is consists of multiple words, like here, square 3 consists of 3 square in print, it's going to go and grab the appropriate, in the case of the fourth words themselves, it's going to go grab the appropriate operations, grab their Lisp code, and then stick it into this let block. Then, after all these are defined here, we created a new labels function. This is a localized scoped function. Remember what labels is, and remember the difference, more importantly, between labels and flet. You could have used an flet here, technically, but by using an flet, you're essentially preventing recursive calls, because remember, labels can create recursively scoped functions, but flet does not. All right. So for folks who are looking at this saying, well, why didn't we use flet to define this scoped function? It's because of that. It's because we do not have recursive functionality in that piece, rather that, but labels gives us that. So we use labels to actually go and create essentially a no argument function whose sole job is to call the functions that we just, that we just grabbed from the fourth environment, and then executes those functions. And ultimately, the biggest question that you might be wondering is well, where's all the other words? Well, like we saw in the code review, we shaken every other word that is not in this particular code block, out of the tree before we actually went through and iterated and got our final piece of code. So what we ultimately did is we got a nice compact piece of code that is executable. If we actually run this guy, and we could try to run this guy, that would be a pretty neat thing to do. If we just run eval on the previous operation, you'll see, oops, that's because I did not do this. Hold on, let me just grab this guy here, yank it, paste, okay. Whoops, oh, right, it's because I'm in the wrong package. Let's do that again. We get the code, if we try and evaluate it, you'll see that it's doing a 3-squared print. So this is a particularly fascinating thing that we've just done. We went through, we created a fourth interpreter. We created a thread shaker for this fourth interpreter. And we went and retroactively, using Pandoric macros, went back into what that fourth interpreter is doing. And we've essentially grabbed the particular words that that are executable, and we were able to actually create a Lisp program that executes them. Let's take another example, just to really bring this home. Let's go ahead and define in our new fourth, because we have factorial already defined. I think I had factorial already. Well, let me go and define it just in case. Here. And then let's go ahead, and what we'll do is just like before, we're going to take a piece of fourth code. We're going to make a complete program, okay, in our fourth interpreter. Think of it like a main function almost. Print name. And we define it. If we eval fourth to Lisp, and I don't encourage you guys to use eval like this, but just for the sake of example, this is useful. If we do eval on our fourth interpreter here, you'll see that again, this is as before. It's going to dump the intermediate results and then ultimately return the factorial of 5. And let me go ahead and do this. This way. Oops. Let me do that again. Okay. Okay. You can see that this will actually go ahead and compile fact 5. There's a couple things I want to close out here, just because the book mentions it, just so that people are aware. There is a couple of differences between Lisp and fourth that aren't accounted for in this particular fourth to Lisp compiler that's inside the tutorial, and it's available from letoverlambda.com. Specifically, we don't have access to the return stack in Lisp, right? So any words that use the return stack cannot be compiled to Lisp in this example. Okay. So that means things like exit, countdown for the hacksaws. Actually, things like exit will not work because it leverages the word, but countdown And countdown does not work because, again, if you look at what our countdown function does is it exits out of the function. An exit, if you recall, is defined as essentially the function that just simply grabs whatever's on the ARM return stack and drops it. Okay, so any word that uses these, because Lisp doesn't have a return stack, they won't successfully compile. Okay. Because of the weirdness of how we were implementing countdown for the hackers, which is a weird way of us, preempting the exiting out of a loop by using an if-then rather than an, let me just go down to it, rather than just right here, where, the conditional determines whether or not we continue looping or we pop out and drop whatever is on the P stack and move forward. Because of this particular structure, this looping will work in Lisp code. Let's see what let's actually see what this code looks like. Print fourth Lisp. Let me do this down here since we have our. Actually, no, this is fine. We can do it up there. I forgot I defined it up earlier. Fourth to Lisp. Our new fourth. And let's go ahead and compile this just in case. Make sure that this is there. Good. This is what this code looks like. Let me do something. So we can actually see the entire code listing. It would be a little bit easier if we do it this way. Okay. So if we look at this code, this is exactly what we would expect for this countdown looping function to do. It essentially broke up our code. Again, it shaked the entire thread to only have whatever's necessary for countdown to actually work. And it grabbed the particular associated functions, and then it created the specific tag body. This tag body is being generated by, if you recall, in here. In our Flubify code specifically, it's in the compiled Flubify. It's actually creating the specific tag body to actually go and structure all the code before it calls it. And it also uses, I think it uses it in this is the only place where it's being used. Here it's actually being leveraged to actually go and figure out the branch statement that it needs to go up to go and structure the looping. So between this and here, as you can see, this is all associated with actually looping through the code, and then this is the exit statement that it needs to do to drop off the code from the P stack. But that's it. I mean, we've essentially went from Lisp to fourth to back to Lisp. That's in a compiled fashion. And again, if we go in, let's go ahead and run this guy. Shift-G. Where are you? Right here. Okay, if we go ahead and evaluate this guy, ooh, that's interesting. Do this. There we go. Slide REPL. evaluate that. It says is not of type real. So there's a couple of oddities there that we should I should go and take a look at. But before we start debugging that particular case, I wanted to also mention a couple of things here. And one is we can't compile words that use compile. So that means meta programs that that like if, then, begin, again, all those at the Lisp compilation stage, we cannot compile those guys. We could certainly, as you can see here, use them to actually go in and compile it in full Forth programs, but fundamentally, the code themselves aren't actually compiled at the time that they're being passed to Lisp. Finally, branch if can jump to pretty much anything, even if it was created inside of a word different than what we're currently executing. But because in Lisp we can only go to other locations within a specific tag body, it won't allow the use of non-local branches. So that's a big difference between Forth and Lisp that you must be aware of. So when you're trying out your Forth interpreter on ANSI Forth programs, if you're not aware that this is a restriction, you may end up getting yourself into a situation that you're where you can't actually compile the code at all. So in the end, this case study that we've been going through basically shows that you can pretty much avoid the majority of the restrictions of these when we were in our Forth environment, but because you're able to use macros to implement the semantics of your particular programming language within the context of your Lisp environment. So in the end, Lisp becomes almost an extension of different types of language-oriented environments, and you could put in different paradigms pretty easily, pretty seamlessly. So I'm going to go and try and figure out what this is all about, and I'm going to stop here if there are any questions. Okay, let's see if we can figure out this final piece of code here, so that we can construct you can see what the issue is here. So we can I could check this guy in, and all this code is going to be available for everyone to check out once I push it in. Okay, let's see here. Wait, isn't that it's a real? But that's freaking ridiculous. That's Forth to Lisp. Forth. Nil is not type real. Let's see something here. What is not of type real? Something's going on here that's wrong. It is... Oh, I'm an idiot. It's because I'm trying to... I have to create the complete program on here. That's why. uh, fourth, fourth, 5, countdown. Countdown 5. There we go. Now this should work. Oops, sorry, not this one. Countdown 5 should work. No, it's not type fourth word. Hold on. Try. I did compile that, didn't I? Forward. Move forward. Ah, okay. I should do this again. As you can see here, the reason why it didn't work earlier is because, again, it has to be a complete program. This is just a function definition, which is why I was mistaken when I was getting that error call. So we taken this complete function definition. If we create essentially a main function that handles all the code that we want to do, we could then use forth to Lisp to generate the Lisp code necessary to complete that program, and then it will go ahead and execute that. So that's it for today. I'm going to open the floor to questions from folks that are on the stream and folks that are on the call. And we'll wait a few minutes, and then afterwards, if there aren't any questions, we will go ahead and move from there.
So instead of eval, can you use compile?
Instead of yeah, I think so. I would think you can use compile, but let's see. And I'll take that back. What is the problem? Simple condition, simple type error. Hold on. Maybe it's because I would have to define a function. I don't think you could use straight up compile because that's not what does compile need again in terms of a Lisp form? Maybe I have to do this.
So maybe you have to wrap it then.
Yeah.
If you wrap,
I think you have to wrap it. You're right. I'm wondering if let's do this. Let me go here. Let's see this. Compile. The first argument is name. Let's call it countdown 5. And then SPC definition, da 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 da. Wondering if I could just do this, fourth to Lisp.
All right, no need to spend time then. Just a simple question.
Okay. Yeah, I don't know. I think you should be able to, but because it is valid Lisp code, as you can see there. It's just that you'd have to do some weirdness here. Maybe create wrapping it around in a lambda so that it gets executed might be appropriate. So something like this is what I'm thinking. If you do lambda that compiled countdown 5 to get this executed, it'll dump it, but it doesn't actually evaluate it. So, well, that makes sense because of the fact that the code itself is just Lisp code that is going to get returned from fourth to Lisp. Yeah, I'm not sure. That's a good question. If you figure it out, let me know.
The reason I asked was because when you evaluated the code before, you got an error. But I think isn't compiling supposed to give you better debugging and instrumentation than just eval?
It should, but I don't believe it. Doesn't look like it'll allow me to take a let statement and just compile it. It has to be within the context of a. Remember, it has to be context of I think a lambda and or a what's it? Actually, it's right here. It's either a lambda or a name or a F definition. Those are the only times you can actually compile something to get meaningful information. Other questions?
What's the plan for post-vacation?
That's a good question. I was hoping that I was going to figure that guy out as I was on vacation. I was thinking. I mean, I'm up to suggestions. I'm really looking into recently to after looking at style warnings complaints about IDEs on Twitter. I started doing some digging myself in just the IntelliJ platform and LSP, which is the language server protocol that someone wrote for Common Lisp, just to see if it's possible to like do a little stream on some of those IDE developments in that space. Other than that, I'm also looking into I have some ideas related to data structures and algorithms in Common Lisp, just to give people a brief overview of some of those again, like a review of it. Not what's available in Common Lisp proper, but rather if you're going to be designing your own data structures and algorithms in Common Lisp, there might be a couple things you might want to be aware of. That's mainly because I purchased functional data structures recently, and I wanted to see if we can go through that and see how we can design some of those things. Additionally, I have a few ideas related to another project, like another like application development stream. But again, these are all like basic ideas that I haven't like really thought through to figure out what would be the right next step to generate. So suggestions, ideas is more than welcome.
Okay.
Cool. Well, I appreciate you guys staying on. Um, I will see you guys in 3 weeks. And for folks just joining us who wants to see the past episodes throughout this series, AFP has just recently consolidated those into a new playlist that's available on the YouTube channel. I will add this new episode to that playlist once YouTube does its thing and finishes, whatever it needs to do for the stream to be visible in my channel. So stay tuned for those, and I'll see you guys in a few weeks. Appreciate it.
Don't forget the merging master.
I just did. I merged master. It's pushed.
And the anaphoric, that needs to be updated as well.
Yeah, I'll do that right now. Let me go ahead and, while I have everyone on, commit exposed self in anaphoric package. Okay, that's been pushed, and the fourth demo changes that we did right now. Implementation of fourth to Lisp compiler. And all that's been pushed. So, looks like we have a couple of questions coming in. Just gonna wait a few minutes here. A couple of folks are just popping in the YouTube channel. Okay then. That was just a simple question that I was able to answer on the YouTube channel. Thanks for those who have joined the live stream. Thanks to you guys who are on the Hangouts. I'll see you guys in a few weeks, man. Everything is checked in and has been pushed into master. So if there are any questions or anything, feel free to ping me on Discord or on Functional Programming Slack, and I'll answer those questions accordingly.
Cool. Thank you.
Thank you.